In this video, we will learn about circular motion. So we will find out in which situation centripetal forces apply and in which direction is centripetal force and the acceleration of the block. We'll find out about different types of centripetal forces that exist, and we will learn a step-by-step instruction how to approach any problem in this unit, as well as solve one analytical problem at the end. So let's start by firstly going over what is the centripetal force. So centripetal force is simply a type of force. It's any force that makes an object rotate in a circle. Any force can be a centripetal force: tension, friction, gravity, etc. Now, it is not a new kind of force, right? It is not like tension or gravity or something like that. As long as a force is able to make an object rotate in a circle, it can be a centripetal force. So it's more of a category of forces than a new type of force. Now, in which situation does it apply? Essentially, in any situation when an object is rotated in a circle. And the direction of this force, this is very important. Since the centripetal force is what makes it rotate in the circle, the direction of centripetal force is always going to be to the center of the circle, of both the centripetal force and the centripetal acceleration. And velocity will always be tangential to the circle. In just a second, we will draw a diagram and I will show this on the diagram what I mean by tangential and to the center of the circle. Now, also very important in this unit is formula for centripetal acceleration. Again, you don't have to memorize this formula because most likely you will be given this on your equation sheet, but just know that anytime we will have F net, right, is equal to ma, in 99% of the problems, we'll have to plug this expression in for centripetal acceleration, that is equal to velocity squared divided by the radius of the circle. Now, let's take a look at different examples where each of these forces, each different type of centripetal force. Now, you could have a situation when tension, let's say, is your centripetal force. For example, right, a stone that is rotated in the circle. I'm going to draw the stone at different points in its rotation, right? So in each of these points in rotation, the tension is going to always be pointed to the center, no matter where I am, right? Because tension here is the centripetal force. So once I have identified that tension is the centripetal force, I know to always draw its direction to the center. And again, the acceleration will always be the centripetal to the center, right? And the rest of the forces will be like normal. So for example, if it's a stone, right, it has gravity that is directed down, right? No matter its position, it's always directed down. Now, gravity can also be your centripetal force, right? The most common example are probably satellites, right? That are orbiting around the orbit of the Earth, or Earth that is orbiting around the sun, right? In a circle. So gravity can totally be a centripetal force. Now, obviously, they're not connected literally, but let's say if this is the Earth and this is a satellite, right? The gravitational force will, once again, will be always pointed to the circle, to the center of the circle. Normal force can also be a centripetal force. So let's say if you have a car, right, that is, let's say, driving in the depression, meaning basically is driving into a hole, right? Over here, when this car is basically moving in a circle, right, the normal force here is pointed to the center of the circle. So the normal force from the road is what makes it rotate in a circular motion. Friction can be a centripetal force as well, right? Let's say, for example, you are driving on a curved road, right? And you feel as if your body, right, is pushing forward. What actually makes you rotate in the circle once your car is basically doing this turn? Of course, is the friction force, right? Your car wants to go basically to the right here, wants to slide out of the road, but the friction, right, is what keeps you on. So the friction here will be pointed to the center. So as you can see, the centripetal force is not a new force that we learned about. It's that any force that we talked about, right, can be a centripetal force. Now that we know what is the centripetal force, we know what situation it applies in, and we know the direction of centripetal force and acceleration are to the center. Let's see how that would change our method for solving the problems. So still, we have the same exact method for solving the problems, right, as we had before. This method for solving that we applied for second Newton's law problems. It basically almost exactly remains the same. We still start with by drawing a free body diagram, except now if we know that an object is moving to the circle, we need to identify what is the centripetal force in this case. So, and we need to label that force, right, and centripetal acceleration to the center, right? Then we're drawing the rest of these forces, right? So what are the forces that are present, in which directions are they pointed, left, right, up, etc., right? Those are all the steps that we have outlined already in our video on Newton's second law, so you should watch that if you're not sure about this. So once we drew a free body diagram, right, taking care of our centripetal force, the next thing we're going to apply Newton's second law in both horizontal and vertical direction, just like we did before. So list all the forces in the horizontal, in the vertical direction, right? And either set them equal to ma or 0. So no changes here. And to part 3, right, in addition to applying to the friction formula, right, plugging in for all of the unknowns and plugging in for the formulas like force of friction, if friction is applicable in this problem, we will basically always plug in the formula for the centripetal acceleration, right? Which is, I will remind you, is v squared over r, right? I would say 99% of the problems we have to plug in this equation right here. We plug in everything else and essentially solve the equation. So as you see, if you already became comfortable with Newton's second law, this method really, our method for solving the problems, doesn't really change that much, right? We just need to know the direction of the centripetal force, essentially, which we now know is to the center, and we need to have this equation in mind, right? That this is something we should look at our equation sheet and plug this for acceleration. Now let's take a look at one of the analytical examples, and let's find out how this method applies to solving actual centripetal force problems. So over here we have a very typical problem that you definitely might see on your quiz or test: a stone that is rotating in a vertical circle. So a stone of mass m is being rotated in a vertical circle with a string of length r. If the velocity of the stone is v, find the expression for the tension of the spring, right? Now, it's okay that there's no numbers in this question, right? If there were numbers, we would solve it numerically, but it will be a really good practice in finding the expression, right? Deriving basically the final answer. So at the top of the circle, halfway, and at the bottom of the circle. Now, again, my first step will always be to draw a free body diagram. So here we have the circle, and we have the stone that is being rotated at different parts of the circle. Now, it is connected to a rope, and it is being rotated in the air. So let's firstly, let's start with this part right here when it's at the bottom of the circle. Let's consider, right, what forces are applied on this stone. So as always, there's always force of gravity, mg, that is being applied. And gravitational force is always directly down. Since the stone is connected to the rope, there is also the tension force that is being directed upwards, right? And the tension force is greater than the gravitational force, right? Because it's supporting it upwards. So is there anything else? There is no normal force, right? Because it's not touching the surface, and the normal force is a force of the surface. So pretty much there's just the tension and the gravitational force, right? What about where it's halfway between? So once again, we have tension force, right, that is pointed along the string, and we have gravity that is pointed directly down. And over here on the top of the circle, we have tension that is pointed along the string, and the gravitational force that is always pointed directly downwards. So as you can see here, the tension is the centripetal force, of course, because tension, right, is always pointed to the center of the circle, right? Let's also label our acceleration, because as you remember, just like forces, acceleration is a vector, meaning it can have a direction. So here acceleration is to the center, here acceleration is to the center, and here acceleration is to the center. Okay, guys, we're almost done solving this problem because, as you remember, a well-drawn free body diagram is like 50% of the question. So now let's find out the expression for each of them. We started with at the bottom. So let's find out expression for at the bottom of the circle. So, of course, we'll start with F net is equal to MA. Right? Let's find out what forces we have here. So we have tension that is going up. So I'll label up as a positive direction. So T is going up, right? Minus mg that is going down is equal to MA. Once I wrote out the sum of my forces, I always plug in for the acceleration. That acceleration is v squared over r. So T minus mg is equal to mv squared over r, right? Plugging in for acceleration. So rearranging for tension. Here's my final answer. So I got my expression for the tension in the rope at the bottom of the circle. Now, similarly, let me find this at the center. So I still start the same way. F net is equal to MA, right? So, of course, now there is the horizontal and there's the vertical direction. So the acceleration is in the horizontal direction. So, let me just apply the Newton's second law in the horizontal direction. Horizontally, we have just one force here. It's just tension, right? And it's equal to MA. Just like in the previous example, right? I'll plug in for acceleration as v squared over r. And this is pretty much going to be my final expression for acceleration at the center of the circle. Finally, I want us to consider at the top of the circle. Where at the top of the circle, right, all the forces and the acceleration are all pointed downwards. So it's minus t, right, because it's pointed downwards, minus mg, because gravity is also pointed downwards, is equal to negative ma, right, because acceleration is also pointed downwards. Or you can multiply the whole equation by -1, and just write that, right, t plus mg is equal to positive ma, right? I could have considered downwards to be a positive direction and just wrote this expression initially. So to rearrange this, just like in the previous problems, I'll plug in for acceleration as v squared over r, right? And subtract mg from both sides to get my final expression for the tension of the rope at the top of the circle. So what I want us to take from this video is the following. The overall method doesn't really change, right? In addition to just understanding that the centripetal force and acceleration are to the center, we just have one more extra formula, but overall our method stays exactly the same. So hopefully this makes sense. Keep watching the videos because in the next few videos, we're going to go over very typical examples that you should definitely know if you want to be good at solving centripetal force problems. Keep practicing, keep watching these videos on your way to an A. Thank you.